This is Zhen Zhang. In this presentation, I will be talking about our recent work, MIX, near linear scaling for training gigantic model on public cloud. This is a joint work with researchers from Johns Hopkins University, AWS, and Peking University. Deep learning techniques has many successful applications, for example, chatbot famous one like ChatGPT, or detecting objects in an image, which is a challenging task in computer visions. And with recent advancement of language models and the contrastive learning in CV, we can also apply deep learning on multiple tasks together like daily too. We can type a sentence and let the deep learning model to paint a picture for us. And there are many more other applications. Deep learning model typically has large number of learnable parameters as compared to other machine learning techniques. And the size grows rapidly in recent years. As shown in the figure, we can see the size grows quickly from tens of million parameters to hundreds of billion parameters. The growing size makes deep learning training compute intensive and memory intensive task. And the size of the training dataset also grows quickly. Thus, nowadays it can take years to train a reasonable model on a single accelerator. To speed up the training, people started using multiple accelerators to train deep learning models. We call this kind of training paradigm as distributed training. Because there are multiple accelerators involved in the training algorithm requires additional communication to coordinate accelerators. We present a data parallel training strategy for illustration here. Assume we have two GPUs spread across two nodes. At the initial phase, two devices will have the exact same model parameters, and we use this joint dataset for the training on each device. Each device sample data from the dataset, start forwarding process, and then backward process to get the gradients. Once the gradients is computed, we have a synchronization step to synchronize the gradients on two GPUs. Then we proceed parameter updating with the synchronized parameters. Using synchronized parameters ensure all devices working on the same model for subsequent iterations. The gradient synchronization phase is typically overlapped with backward computation for efficiency purpose. Despite the simplicity of data parallel training, each GPU has to have a complete copy of the model states, which includes model parameters, gradients, optimizer states. Thus, the size of supported model is limited by the memory capacity of a single device. To support large model training that requires memory exceed the capacity on a single device, and to keep the simplicity of data parallel training, the 0.3 data parallel training is proposed recently. We take a two-layer model as an example. The 0.3 data parallel method partitions the model states to all devices in the cluster, while the structure of the model is maintained on each device. We use different colors to denote different parts of the model parameters. Shown in the figure, each device holds a quarter of first and second layer. To proceed the forward computation of the first layer, devices needs all-gather communication for first layer. After the all-gather, each device has 4 parameters of first layer, and we can proceed the forward computation. After the computation of first layer is completed, we release the memory space for first layer. Then we start all-gathering for the second layer, so on and so forth. Compared with vanilla data parallel training, the large model training with 0.3 data parallelism needs more communications, as discussed here. The mentioned 0 data parallel training solution is general, but not perform very well on public cloud. Here, the generality of the solution means the no-code modification for the model implementation, and it can support different kinds of models, including NLP models, CV models. In comparison, model parallelism solution requires specific primitives to re-implement the model. The performance means the throughput and the scalability. Based on our measurements, we found the performance issue is mainly due to large communication overhead. To bring down the communication cost, we first need to know the reason that causes communication overhead. 0.3 partition model states onto all devices. Every time a parameter is used for computation, we need to fetch the parameter from all devices. In other words, the number of participants in each parameter fetching is large. We define the size of the participants as a communication scale. Large communication scale introduce 3 main factors that lead to high communication overhead. First, communication can include distant nodes that including slow links. Secondly, the efficiency of algorithm decreases with more participants. Lastly, data transmitted is larger with more participants in the communication. All three factors contributing to the communication overhead. Here we have some measurement results to justify the claim we made. X-axis represents the size of the message. We measure the throughput of all gathering in different sized cluster. We can see the bandwidth decreased significantly for small to medium-sized messages. These small to medium-sized messages are important to efficiently overlapping communication and computation. As mentioned, the large communication overhead is relevant to the communication scale. In response, we propose mix, which follows the core principle that minimizes the communication scale as much as possible. We introduce three components to achieve this goal. First, scale-aware model partitioning. Second, we have hierarchical communication strategy. Lastly, to hop gradient synchronization schedule. Here we give a motivating example for scale-aware model partitioning. Assume we have a model with 10 billion parameters. Training using Adam optimizer requires about 160 GB memory for holding the model states. A node with 8 GPUs with 32 GB on each GPU can have 256 GB memory in total, which is enough for training the model. Thus, it is not necessary to partition the model state to all devices for certain models. Next, we describe the scale-aware model partitioning. Assume the model is trainable on P devices. For a cluster with N devices, we divided them into N divided by P groups so that each group holds a complete replica of the model states. In other words, we partition the model states within every P devices. The figure here shows an example of P equals to 2 and N equals to 4. We define the ranking holding the complete replica as the partition groups, and the ranks holding the same part of the model as considered as replication groups. The scale-aware model partitioning brings two noticeable benefits. The communication efficiency is guaranteed because when we increase the size of the cluster, the size of the partition group is fixed. If the partition group size is small enough, say within a computing node, then we can leverage the PCIe or NVLink for communication within each partition group. Next component in Mix is called hierarchical communication. Assume we partition the model states onto P devices. These P devices can span across multiple nodes. The bottom assume P equals to 4 and each node has 2 devices. Assume a ring-based vanilla collective communication among these 4 devices. The data transmitted across 2 nodes is P minus 1 divided by P times M, shown in the graph. And the P is equal to 4 in this case. M is the message size. In hierarchical communication, we split one communication into multiple smaller communications, and we execute communication in 2 stages. Assume a partition group size is 4. We first launch cross-node communication in parallel. Then we launch the intra-node communication in parallel. As shown in here, the cross-node traffic is reduced because each communication only has 2 participants. The benefit of this strategy is that inter-node data volume is reduced, as shown in previous example. More specifically, the factor of message size is reduced from P minus 1 divided by P divided to P divided by K minus 1 and the divided by P over K, where K is the number of devices on each compute node. Based on our analysis, the size of the data is reduced around 11 to 46% for 10 billion model, 10 billion parameter model, and 50 billion parameter models. The last component is two-hop gradient synchronization. In large model training, large batch is divided into multiple smaller ones because of the memory constraints. We call these smaller batches as macro batches. We accumulate gradients for each macro batches to get the gradient for a large batch. For computation of each macro batch, we call it macro step. And for each macro step, we synchronize the gradients within each partition group, shown in the figure. The reason to have gradient synchronization for each macro step is to release memory space for gradients. We proceed the macro steps until the last macro batch, where we reach the gradient accumulation boundary. We need to synchronize the gradients among all devices. We first synchronize the gradient within each partition group as well, then synchronize the gradient within replication groups. The benefits of this is that communication efficiency is guaranteed when we scale up the size of the cluster, as most of the gradient synchronization happen locally in partition groups. Next, we present the evaluation results. In evaluation, we first evaluated the performance of mix, and then we studied the effectiveness of each component in the system. Lastly, we examined the fidelity of system implementation. In this talk, I will present the result of the performance only. The evaluation is conducted on AWS instances. We evaluated the system on two types of cloud instances, P3DN instances and P4D instances. For P3DN instances, we have V100 GPUs and 100 gigabit network, and P4 instances have A100 and 40 gigabit networks. Both of them have NVLinks for internal communication. We mainly evaluate two matrices through throughput and scalability. Throughput measures the samples per second rate in training, and scalability is defined as the throughput of a cluster divided by the starting throughput, where starting point is the throughput of a smallest cluster that can train the model. I will present three parts of the evaluation results: scalability on 100 gigabit networks, scalability on 400 gigabit networks, and a performance comparison to Megatron 3D. In this evaluation, we focus on the scalability of mix for different sized models. Shown in the bottom figures, we present the result for two BERT models. One has 15 billion parameters, another one has 20 billion parameters. The x-axis of the figure denotes the size of the cluster. The y-axis denotes the throughput. The outside rectangular denotes the linear scaling with respect to the smallest cluster. The smallest cluster for training 15B and 20B model is 16 GPUs. From the performance perspective, mix achieved near linear scalability, and it is up to 2.882 times faster as compared to 0.3. In the evaluation for 400 gigabit network, we use same training setups. As shown in the right side, mix can achieve near linear scalability as well, and it is up to 2.21 times faster. We have also conducted a case study for training a model with 100 billion parameters, and the mix can achieve near linear scaling as well when we scale from 128 GPUs to 512 GPUs. The scalability is about 1.3 times better than 0.3. We also compare our system against Megatron 3D on P3DN instances. For fair comparison, we disabled customized kernels on both sides. We followed the takeaways from Megatron 3D paper to tweak the performance of Megatron system, and we listed the configurations in the right table. The performance numbers show that our system is up to 31% better for a BERT model with 10 billion parameters. Another thing worth to notice is that Megatron is a model-specific design that cannot generalize to other type of models, while DeepSpeed and our system can train other type of models. Performance comparisons are shown in the right side for a wide ResNet model. In summary, existing 0.3 system cannot perform well, specifically training a public cloud environment with more restricted bandwidth, and the root cause is the communication overhead. Mix reduces the communication overhead by minimizing communication scales, and we design an implemented system that can improve training performance significantly. And the implementation is open sourced, and it is now merged into the DeepSpeed master branch. Thank you for your attention.